Hi, my name is Murthy Upmaka. I work for Keysight Technologies. In this video, I will introduce a new feature, EMLink, in SystemVue 2021. EMLink helps us increase the efficiency of an RF board flow. As can be seen here in this picture, there is a new way to go beyond the spreadsheets. Let's say we have completed a lineup as shown here and performed optimization, analysis, etc. to arrive at a required specification. After that is done, the natural progression is to go and then build a layout for those parts, knowing their footprints, knowing the interconnect details, and knowing the substrates, etc. Once the layout is done, one can use an electromagnetic simulator to simulate the performance of the layout itself without the parts, of course. The output of a electromagnetic simulation will be a multi-port S-parameter file. In this case, in this particular case that we are going to discuss, it turned out to be a 26-port S-parameter file. At that time, we can bring the 26-port S-parameter file into SystemVue, back to SystemVue, and introduce the interconnect characteristics that from the 26-port S-parameter file. Once we do that, the new feature, EMLink, allows us to predict the coupling of energy between traces, one area of the board to another area of the board, in the first phase along the path that we are going to define. Once we do that and then identify the leakage problems, we can go back to the layout and then fix the layout and then continue analyzing an EM analysis and bring back the results. And then we can continue to do this until we are satisfied that the leakage due to radiation is well contained. Once we are done, we can progress to the next step of testing the lineup with a complex modulated time varying signal. In this particular case, we are showing a chirped signal for a radar application, but it can be a communication signal as well. The advantage of this flow is that once we build a good model for the RF lineup, it can be used to go to the next level of a system simulation, and the high fidelity model will make the system simulation much more accurate. Let us see how this flow happens in the tool itself. As can be seen, the lineup is here, the initial lineup, and the modeling of each one of these parts with the available vendor parts are shown here. Once this is done, one can go on to building a layout. We should also note that if you want to get familiarized with building up a lineup, doing analysis, optimizing for the performance, you can visit the YouTube videos. We have a lot of videos on the YouTube, especially in this playlist. If you go and then specifically look at 15 to 22 videos, which are typically 5 minutes in duration, you will get a great picture of performing RF lineup in Spectrasys. If you also want to get a detailed workshop, you will be able to get that from Keysight Knowledge Center by searching for EMLink. As mentioned previously, we can build the layout anywhere and then import into ADS layout environment and perform electromagnetic simulation. This is only a picture of what we have done in advanced design system and performed a 26-port S parameter uh, analysis using the electromagnetic simulator called RF Pro. Let us examine how we can harness that 26-port S parameter file to get deeper insights into our RF lineup. Now, once we bring the 26-port S parameter file, we can place the interconnects between parts from the 26-port S parameter file. In order to do that, you have to select a net, right mouse click, insert S parameter interconnects, and once you say that, you can point to the S parameter file that was simulated in electromagnetic tool. And if you click OK, you can see that there is an interconnect introduced between the parts. Now we have to appropriately specify the interconnect location in the S parameter file. In order to do that, we can double click that and we can use the names that were there in the S parameter file header. And those names are in the drop down list here. So the input port for this trace name is RFin and the output port is AMP2in. Once we do that, you can see that it introduces the appropriate S parameters for that interconnect. So we can go on repeating this insertion of interconnects along the chain on the entire schematic, of course. We have already done this in another schematic, as can be seen here. All the interconnects are introduced between all the parts. When we do this, you can also notice that we get an interconnect table. You can see that interconnect table. You could have used this interconnect table itself to map the traces, interconnects, as shown here from the S parameter file. Once we have done this, at this point, if you run a standard path analysis along this main path, let us say, you will be able to get the behavior of this main path, that includes the transmission characteristics of each one of these interconnects, which are S11, the mismatch at the input, S22, the mismatch at the output, S12 and S21 of the interconnect. So those will reflect in the path measurements if we perform an analysis. But what if there is a radiation by this trace to all the other traces, or all the other traces radiating to this trace? How can we capture and then how can we get an idea about that radiation? That is the new EMLink feature in SystemVue 2021. In order to do that, we have to go into the analysis, go to the paths, and then we have already created a path 1, for example. And then if you edit that path, we have a new path type called layout modeling, as can be seen in the drop-down list. And you have to specify the S parameter file that is used for the layout representation. And if you check all these 3 boxes, you will get the measurements corresponding to this EMLink. So once we do that and perform the analysis for path 1, which is the main path starting from this source, ending at the output port. Now, if you see this, all the measurements that if you are familiar with Spectrasys, you would know that all these measurements would anyway come through. The new measurements that have come through now through EMLink are under this folder EM. So we have measurements like EMEPP. What it means is electromagnetic port power. from the electromagnetic analysis. So if you see that node names 1, 4, 14, starting from the input source going up to the output port 2. So what it says is this is the amount of radiated power appearing at that node radiated by all the other traces along the path. So if you see that carefully, you will see at some points along the chain, there is significant radiation. For example, at node 25, minus 10.6 dBm is appearing at node 16, minus 12 dBm is appearing, etc. So what we have captured in this analysis is the radiation from one trace to the other. If you want the full picture of the radiation from one trace to the other, since we have 20 ports along the main path, there will be total values of 400, 20 by 20 matrix that describes the radiation coupled energy interactions between one port to all other ports. We also have another measurement called EMCI, carrier to interference ratio. In this case, coupled energy to the required signal ratio. So if you scan this, you will notice that at node 16 is the most troublesome place where our coupled energy at the node 16 is so high that it is only 3 dB away from the desired signal. This is really a troubling observation for node 16. Let us also see the same thing in a graph. So in a graph, we could plot the desired channel power, DCP, and the coupled energy, EPP. So the red trace is the desired channel power. We started with minus 12.4, we ended up with 32 dBm. This electromagnetic port power started very low. The difference between these is quite high, so we can probably ignore at most places, excepting that when we come to this node, it's only 3 dB difference between them. There are other nodes also as well, which are also causing problem. Here it is about 5 dB, and then here, of course, it's going to be quite a big difference, like 26 dB. So we are interested in places where the coupled energy is significant compared to the desired signal energy. At that frequency, of course, the path is always with respect to one frequency. This is the desired signal frequency. So this is an area of problem we found. But then if we ask ourselves, what is causing which other nodes, which other trace is radiating significantly to this node 16, and then how to find out? We can do a little bit of post-processing in SystemVue. It allows accessing the variables in the data set and writing equations. In this case, it's all MATLAB syntax, excepting that there are some specific functions specific to SystemVue. That's why we call it as MATLAB script. So you can see that we accessed, all that you have to do is we define the path and then we access the data set of the path. So you have to specify the data set name here, and you have to specify the number of nodes along that path. And you can also specify what is that coupled energy to desired channel power ratio. If that ratio is very low, if those two are separated by 30 dB or 50 dB, whatever is your requirement, we can ignore anything below that. So we put a threshold here, minus 30 dB. The rest of the code just runs smoothly once you specify these three, and then provides us a table named as ranked leakage ratio table. You can see that the sorted values of the EPP ratios here, and then you can see that the uh, the interconnect 11, which is the node 16, is a problematic area. So which other node is significantly causing problem to this? Obviously, the output of the RFAMP4 is causing a serious problem, and ranking by that interconnect 13 is also causing problem at interconnect 11. D3 is causing problem at interconnect 11. Interconnect 6 is also causing, but with a diminishing values. So can we collect all the contributions of the other nodes at interconnect 11 alone? We can. Again, just simple processing would allow us to extract that information. So we have done this. This table is now available to us. Once we have the table, we can go back to the layout and then pinpoint where the problem is. For example, this is the interconnect 11, and this is RFAMP4. So the node RFAMP4 is connecting from output to the input. This is interconnect 16. This is interconnect 11. Sorry, interconnect 11, and then this is interconnect 16. So the coupling from 16 to 11 is a serious problem for us. Once we can go back to the layout, fix that problem, and then bring back the results and do the analysis to check if the problem has gone or the problem is reduced. So this is how the EMLink in SystemVue allows us to identify and fix the problems. So it addresses two things. Number one is where is the problem? Number two is what is causing the problem? We have answered both the questions through this feature in SystemVue 2021. This is the first phase of the implementation of this feature. What we have done is we have been able to identify the radiation from all the traces to any one of these traces along this path. What we have not shown is the influence or radiation from the LO section, local oscillator section of the board. In future, this will be automated, and then those contributions will also be included in the main path. For now, we can do a little bit of post-processing to get an idea of how much of the yellow leakage is appearing along the main path. To do that, all that we have to do is we have to define two more paths. One path going from yellow to back to the source. So the influence of the yellow will be included in this section of the main path. And we can also define another path going from LO to the output node so that the leakage from the LO section will be accounted for in the section that is beyond the mixer in the main path. We have precisely done this. We have done that through a script, again, MATLAB script. You can see that the script allows us to access the data sets, post-process them, and then extract the information the way we want. Once we have done that, we can plot the desired channel power, the EPP along the main path, and the LO leakage. So as you can see, this was the problem along the main path we have seen. At the time, the EPP was only about 3 dB down, and then the LO leakage is down by about 25 dB from there. Is that enough? If it is not enough, we have to go back and then fix that problem as well. And also notice that there are places where the LO leakage is more significant. For example, at node 5, the LO leakage is only about 20 dB down. So it looks like there are some issues with the LO leaking into the main path. Please note that this leakage term is not through the isolations of the part. It's not through the conduction through the transmission lines, but it is the radiation from the LO section to the main section. So one has to probably use the techniques of channeling and then covering, put the proper parts into the channels, mechanical channels, and then isolate them. We're not going to discuss a solution, but we are going to highlight the problem only in EMLink. To summarize, as we can see, we have a lineup, initial lineup, and then we arrived at the layout. And then we brought and then performed the electromagnetic simulation on the layout in ADS RF Pro. We brought the multi-port S parameter file and then inserted the interconnections, pretty straightforward, with the tool providing a very easy mapping of the interconnects into the main path and the LO path as well. And then we performed post-processing and identified the problematic areas. Not only the area where the problem is, we also found the offending nodes that are radiating into that particular area. Once we have done that, we were able to rank it and then find the problem. For example, this is the troubling node where the contributions are coming from all other nodes. We could go and then fix the problem at the time. We also interested in understanding how much LO leakage is happening into the main path through radiation. So we wrote another small script here, and then that gave us the ability to plot the LO leakage into the main section as shown here. I hope you will exploit this feature EMLink into your system design and achieve efficiency and reduce the number of board spins. Thank you very much for watching this video.